our next speaker with morning session is Theshani Nuradha. She was about the Pufferfish privacy.
Let me start with thanking the organizers for putting this conference together. So today I will be speaking about the flexible privacy framework for content systems. So this is a joint work with Siddhartha and Margaret. To start off, let's consider the following scenario that we are collecting data for a survey, and the motivation, the objective behind the survey is to understand the overall health condition of the people in one country. And then we are considering about the privacy of our individual data. Let's say we don't want to reveal whether we have a particular disease or whether we are taking any particular drugs or anything. So it's more individual data that we want to protect. In that sense, we can use this is a statistical privacy framework which has been quite used in the context, especially even in US census when releasing the data. So what differential privacy does, in high level, it will answer aggregate queries like, let's say for this example, it will be the overall health condition of people, and then while keeping the individual records private. So while keeping our whether we are taking drugs or whether we are having particular disease. So let's consider another survey where the motivation, the objective is the same thing, that we are looking for making some high level understanding about the health condition of the people. But now, in this context, we can think of the people who are giving the data could be hospitals. So what they want to ensure in this case is they don't want to reveal the mortality rate associated with their data. So this is a different context that hospitals might be releasing the data, but they don't want to highlight or reveal the mortality. So in that context, can we use differential privacy? So this differential privacy is kind of designed in a way that it provides privacy for individual records rather than any function of the database or anything like that. So that is one of the limitations that is associated with the design of the differential privacy. And also, let's say we have some kind of domain knowledge associated with us that we can incorporate into the system. In that case, also differential privacy is a worst case that, in a sense, a worst case guarantee. So we will not be able to encode domain knowledge. So in classical space, there is a versatile privacy framework which is known as Pufferfish privacy. So what it does is it provides a framework that we can customize which information is regarded as private, and also it explicitly integrates what kind of distribution assumptions that we have. So the domain knowledge will come as a form of a distribution assumption. So this is what we have in classical space. So now let's move to quantum data and what is available right now with that. So for that, a generalization to quantum, which is quantum differential privacy. So to consider that, let's consider two states, rho and sigma. And we want to make those states indistinguishable. So in that sense, we want rho and sigma to be classified as some kind of neighbors. So this neighborhood relation can be arbitrary. You can think of them as some kind of closeness in systems, or like some equivalence of the subsystems, which is kind of captured by process time distance or border one. And those like this, for this talk, will make this rho and sigma to be any arbitrary. They are satisfying an arbitrary neighborhood relation. So to see what formally it says is, let's say we have a quantum algorithm. You can think of it as a quantum channel is satisfying quantum differential privacy if we have the states rho and sigma, and then we pass it through a quantum channel, and then the adversary does some quantum measurement on it. So what we want to ensure is, after an outcome, the probability of getting a specific outcome when the input is rho and when the input is sigma to be close enough. So this is also having the symmetric property that the classical differential privacy is having, because rho and sigma are neighbors, so we can think of as sigma and rho are also neighbors. So this is kind of a generalization to what Lemon talked about in classical privacy. And the special thing is that we have to make sure that this arbitrary, like the closeness in distributional sense, respecting epsilon and delta should hold even if the adversary apply any kind of measurement. So it should value for all measurements. So in words, what here quantum differential privacy would guarantee is that for all pair of states that are classified as neighbors, we want them to be approximately indistinguishable, approximately because of this epsilon and delta parameters, and then this should not be identified by all possible measurements. So thinking of this setting and having some idea of what we had in the classical space, so we asked the question of what kind of things the quantum differential privacy might not be captured. For that, let's consider the following example. So we have a state space with 4 states, rho1, sigma 1, rho2, sigma 2. So what we are interested here is, let's say we want to hide a specific property of the state. Maybe the secret correlations associated with the state or the entanglement, if they are bipartite states, the entanglement associated with those states. So if you want to hide that, yes, we can use quantum differential privacy in this case if we want to hide between A and B. But what we have to do is we have to declare rho1 sigma 1 to be neighbors, rho1 sigma 2 to be neighbors, and rho2 sigma 1 and then also rho2 sigma 2. So then if we do that, we will get what we want. But what we exactly want to hide is the specific property value. Then what we want to distinguish between is the sets R and T. So what we want to distinguish between is the set rho1, rho2 with sigma 1, sigma 2. So the thing that we want to make is we might be having flexible secrets. So the addition here is the secrets containing collection of states rather than one single state. So one single state would be a special case of that. And also we might be having some idea of what kind of states are actually possible to have, and then like the likelihood of observing those different states. For instance, let's say we know from our physical system the state sigma 1 might not be appearing there. Then what we want to hide is rho1, rho2 collection with sigma 2. So in that case, we have to think about that as well. And most importantly, in the quantum differential privacy, this is kind of a new addition which doesn't appear in classical space as well. So then the problem here is that the quantum differential privacy, we have to ensure that these two states are indistinguishable for all possible measurements. But let's say this state, the particular state has two subsystems which are particularly distant in physical space, and how they are going to do the measurement. Then they might be not, the physical constraints might be towards not having joint measurements. So what they could do is having local measurements and then do some classical communications and do the processing. So how are we going to encode that into the set? So the goal behind this work is designing a flexible privacy framework for quantum systems. So we, inspired by the classicals naming, we also named this proposal for this flexible privacy framework as the quantum Pufferfish privacy framework. So to see what are the ingredients, let's say first we will have a set of potential secrets. So what they are is what we actually want to hide. So if we see an example related to the earlier setting, what we want to hide is related to the collection of states having the same property value. So in this case, it will be the collection of such states, Pi, and then we want to make particular sets to be discriminating. So we want to declare that what pairs of secrets we need to make it indistinguishable. So and then here also we have the symmetry property. If R and T is in the set Q, T and R also should be there. And for this particular example, so these discriminating pairs would be Pi and Tj. We collect two Pi and Tj, which are I is not equal to J, and then put them together, and then they will make the set of discriminating pairs. And how are we going to put the assumptions regarding the likelihood of states? First, then we will go with the set of data distribution. How we are going to put that together? We will sample the random variable from the distribution Px, which is included in the set data, and what exactly rho x models is the density operator that is randomly chosen from the distribution Px. And last but not least, we have the set of possible measurements. So this set would consider the subset of measurements possible under physical, legal, or ethical constraints. So now we have this framework. So putting them together, we will come up with this. We have come up with this particular definition. I will go over that now. So what it says, if we want an algorithm, a quantum mechanism or a quantum channel to be epsilon delta quantum Pufferfish privacy QPP in the current framework where we have the recipe ingredients to be set S, Q, theta, and N. And what we want to ensure is, I'll say what rho R and rho T next, but what we want to ensure is to make rho R and rho T indistinguishable in a sense for measurements which is under the plus theta, the plus m rather than all possible measurements. And then what rho R and rho T, those will be conditional average states. So what they are is, if you consider the set R, and then rho R corresponds to the condition on the distribution Px, and condition on the distribution Px, as well as the set R, we will have conditional average states, and we want them to be indistinguishable. So this might be a little more of a technical criteria, but let's see about what it actually guarantees in the semantic meaning, which is important in privacy states. So what we have is we have state rho x chosen according to the distribution x, x sampled from the distribution Px, and we input into the quantum channel A, and adversely applying measurement from the set M on the channel, and then seeing this output A rho x. What it draws, the conclusions that they draw should be the same regardless of whether rho x belongs to R and T. So this what this ensures is that we are hiding the fact that the set R and T are designed in a way that we have particular properties to be hidden. So if we hide the fact whether that state is belonging to that set, that makes the property hidden. So one thing to note is the privacy frameworks that have been existing are special cases of this framework by choosing specific ingredients to this QPP framework. Quantum literature privacy, classical Pufferfish privacy, and also utility optimized privacy models. What they are is maybe this is not exactly appearing in quantum for now, but in classical space, utility optimized privacy models have been there, but they are not a special case of the classical Pufferfish privacy. But with the additional set that we have, the set of measurements, we have the potential to include that as a special case of our quantum Pufferfish privacy framework. So before moving to the next section, I want to make sure that we are on the same page on terms of privacy and safety. So in cryptography, what we assume, we have Bob and Alice and Bob, and then Alice shares some information with Bob, with the understanding that Bob is a legitimate party. But the difference comes there in privacy is that this legitimate party assumption is not there. So even the Bob can be nice and bad at the same time, so you don't trust them. So this is the distinction between what existing in cryptographic sense and privacy. So now I will move towards some information theoretic connections to this privacy framework. So this is an information spectrum divergence which was introduced by Nilanjana and Tariq in terms of information spectrum divergence with some second order analysis. So what it says, if we choose the minimum lambda that achieves, if we take rho minus lambda sigma and then take the positive eigenspace and take the trace, And if we bound that by delta and then take infimum of such cases, it will be this information spectral divergence that I will call as clear divergence afterwards. So what we can show is that we can provide an equivalent combination of the QPP framework for the special case of, let's say we have a set of M with all possible measurements, then what we arrive at is a constraint which associated with divergence. So to see more in an operational sense, so the operational interpretation to this quantity can, one of the possible operational interpretation is the minimum epsilon that can be achieved for fixed delta via this indistinguishable decondition. So the indistinguishable condition that we showed earlier. So this provides an operational interpretation to that quantity. Now we have an operational interpretation. So this provides a connection from this framework to this specific divergence. Now this calls for further exploration of this quantity because what we learn from there will give us more potential, or like will give us a chance to make progress around privacy as well. So we derive like real divergence can be casted as a semi-definite problem, and using those we can show that the data processing in for every positive place within map we have the data processing, and also considering the convex combination of states we will have joint quasi-convexity, and also we have quasis of additivity. So what in this case we have some kind of, it's a tensor product of rho 1, rho 2 with sigma 1, sigma 2, and then it is bounded by individual terms, with some further term there. So this we will see why we are reaching out to this. The extra term there, we want them to be independent of the individual terms. So we will see why we exactly want them to be in the operational sense. And to note that this might, we don't know whether this is right. So this is an open problem to see whether this actually satisfies subadditivity, or else like whether these things can be improved. So the proof that we followed is we had a relation of the real divergence to a smooth max relative entropy, and then smooth max relative entropy satisfies subadditivity. So that's how we transition from there. So, and then using the SDP also we can get some kind of subadditivity in quasi sense, but the things that we got is not independent of the individual terms. So we will see why exactly this is important in the slides. So now we are understanding the properties of the privacy framework. So this is something which is well established in the classical space. If we want a particular privacy framework to be a proper privacy framework, it should satisfy following properties. First, for post-processing. So what it ensures is passing an output of a QPP, like private mechanism to a channel, it should still preserve privacy. And then what convexity is, like we have several private mechanisms and we choose them randomly, and still that process should be should satisfy privacy. And now we will see composability. What is composability? We have let's say we have parallel mechanisms, parallel channels which are independent. Now they are not adaptive, so we will have independent input to all these mechanisms A1 to AK, and then what we want to ensure is after applying that and then considering the composed mechanisms, it should satisfy the privacy condition. And also we also looked at something related to adaptive composability. So in this case, what we looked at is we have, let's say we have applied the one, and then we do a quantum instrument, and then feed that quantum instrument classical component to the next. Depending on that outcome, we choose the next outcome. And we also have some results in the space of correlated input sets. And this can under different conditions, this can be true for quantum properties as well. And we know is for all possible measurements, the proofs can be derived using the properties of real divergence. So this is how we could the connection that we built with the quantum information theory tool help us derive progress in the time systems. So to know that the composability is little different from classical space. So the differences, like you are welcome to the Canada papers to see what exactly the differences are. I will show one of those. First is if we consider parallel composability of two mechanisms, and then under product measurements, in the sense like we apply measurements on each of those mechanisms separately rather than a joint measurement on the composed mechanism. So what we can arrive at additive privacy guarantees. But if we consider all possible measurements, that means a joint measurement, what we could arrive at using the property of the forces of conductivity that we have derived for the joint measurement case in real divergence, what we have is additive terms plus some supergitans, and this is why we are looking for something which epsilon and delta are kind of independent and see how these things can be derived. And so this provides an operational interpretation to having subconductivity or like forces of that some type characterizations will make progress in parallel composability results, which is kind of important in privacy setting because if we have just one mechanism and then get data, but if we want to see it in large scale, we will have to compose several mechanisms. So this is one kind of bottleneck which might be arising in the when we are doing quantum differential some information theory task in quantum differential privacy, because composability is something that we will have to go through in most of it. So we kind of we can think of this following observation as a distinction between classical and quantum cases. Maybe this can be improved in some sense, but what we have for now is but these joint measurements can infer more information. So that's why the privacy can be degraded. So this is kind of the operational integration that we have based on the current results. Now we will look at once we have a privacy scheme and then we look at the properties next is what kind of mechanisms would satisfy privacy. So using the depolarization channel, so we will have the channel E and then we will compose it with the depolarization channel. So we can show that this channel is epsilon QPP. In this sense, we have fixed delta, but we can have some similar results in the case of when delta is not 0. So what I want to show here is that the appearance of the value k, this k is capturing the domain knowledge that we have. So in the sense, the measurement, so this k value is depending on what kind of measurements that we can do and what kind of domain knowledge and what kind of flexible secrets that come into the picture. So having all these terms and in mind, and for the previous one, I should know that this is just a sufficient condition. So it's an open question to see what are the sufficient and necessary conditions. So that means we need optimal mechanisms in this case. So now, why we are looking at auditing privacy? So what is auditing? Is let's say we have a physical system and we don't know whether it's private or not, but we want to see what it is. Also, we can think of that as somebody gives us a system and say this is private, and how do we trust them? So in that sense, we can audit. So what it ensures is to detect violations in privacy guarantees and reject incorrect algorithms. So this is a relatively new topic in the classical space as well. So recently people have used information theoretic like how we can use information theoretic arguments to make progress in this direction. So what we do there is if we have a privacy constraint, privacy requirement to satisfy it. So if it is not efficiently computable, or else if we can't efficiently say that this is satisfying this privacy constraint, then we go for a weaker privacy notion that is efficiently computable, and then we do the auditing there. But the problem associated, and then what we can ensure is that if a mechanism is not satisfying a relaxed privacy notion, it implies that the original requirement is violated. But we don't know the otherwise. So that the pitfall of this approach is the impossibility of quantifying the gap between the original and the relaxed privacy notion. So why are we looking at this in this phase is now with quantum algorithms and the developments that have been made there, we ask the question, can we do auditing without translating into another privacy notion? So the goal behind this is auditing without translating into a relaxed privacy notion. One possible way would be like, if we now we have formed this connection to the real damages and we have the STPs, so why not we will try out computing that STP. But the problem is like the runtime will be polynomial in dimension, but exponential in number of units. So what can be done otherwise? So in that case, we can use some kind of connections related to trace distance estimation techniques. So why we get it is because of another equivalent formulation which is given for quantum differential types by Christoph and others. So what with that formulation, so that even we can formulate the constraint that we have the quantum Pufferfish privacy also to this. And like for this special case, let's consider quantum differential privacy. We have only stage 2 and sigma. In that sense, if we want to audit, one possible way is thinking about this hockey stick divergence and the trace norm there. So can we use the techniques that have been developed in trace distance estimation to estimate this following trace norm, and then it might be a possibility of auditing. So, so we have looked at several algorithms that have been developed in that sense, and we modified them to suit our setting, and then we have some quantum algorithms which we can audit for privacy. And also, it's important, like we are auditing, but do we know how good we do? So in that sense, we want some formal guarantees. So we have some formal guarantees on type 1 error, but like we cast this problem to hypothesis testing problem and then analyze its type 1 error. But the problem would be we have to also analyze the power of the test. So these are it's an open question of how powerful the test is. And to summarize, we propose a notion of quantum Pufferfish that provides a flexible privacy framework for quantum systems, and we have an operational implementation for the real damages and static properties. And I didn't go to the characterizing privacy utility trade-offs, but we can use those techniques there, and then we, in that sense, we had to come up with a utility metric that has some operational sense, meaning, and then we went out with that, and then we have mechanisms, and we have a methodology to audit quantum privacy, and also we have variants to some kind of, what kind of variants that we can come up with, especially if we have entanglement, how are we going to put that into the picture, and then whether we can see some importance through the entanglement. And then we have some connections to other privacy frameworks and the information theory tools and quantum fairness. And what we do is like putting all those two things together to a unified framework. So as open questions, we will be having so we will have this subadditivity problem of whether if we can show something in the real divergence, whether it's subadditive or whether we can improve the bounds, that will make progress in the first in this space as well. So we believe that our work is kind of connecting information theory and quantum algorithms together. So the progress is made in those things will make progress in understanding privacy of the system.
So we build on or we modify this graph, the previous privacy definition that you presented at the beginning. I don't really understand this. I mean, privacy can often be formulated in terms of indistinguishability between states, or it can also be formulated sometimes with the worst case measurement and probability. But in this case, you assume that the states are already known to be epsilon close to each other, and then you have to refine requirement for those states of the measurement, given giving probability in distinguishability time. So how
So
is that?
this is like not necessarily like we can think of them as a parallel thing. So we have a recipe where we can declare these are the things that we want to hide. These are the, let's say for a specific example that we don't have any additional assumptions on the states, occurrence of states. For that case, we will have states as the labeling states that we want to hide in the set of Q, and the set of M will have the measurements. So this is not like we are fixing one thing and we formulate discussions such that it should hold for all states as well as for all states in that set Q, as well as for all the measurements. If we can fix one, like you can think of fixing both the ways, like we can fix the states and then think of whether it should satisfy all measurements, or like we can fix a measurement and think of whether the states are indistinguishable. So this is not like we fix one thing and the other. So we feed this whole thing into the system at once and then observe what we can.
Okay, it seems it's about time, so next thing is Theshani and all the speakers.